All right, chemistry, this is the first part of a two-part lecture for Chapter 6, Sections 3 and 4. We're going to start off with Section 3, Ionic Bonding and Ionic Compounds. Your objectives for this section: differentiate between a formula unit and a molecular formula. They sound very, very similar, but there's a fine difference, and it's an important difference, so make sure that you can tell the difference between those two. Describe the arrangement of ions in crystal form, aka a lattice structure. That's going to be an aspect of ionic solids, and you're going to need to be able to describe that. Describe the ionic bonding process. All right, we know what the crux of an ionic bond is. Describe that as a process from start to finish. Define lattice energy and describe its significance. And if you remember from last section, the idea of bond energy, this is going to be pretty closely related, not the exact same thing. It certainly deserves its own term, which obviously it is, but it's going to be very closely related. And then lastly, distinguish between the characteristics, and by characteristics I mean melting point, boiling point, and electrical conductivity, also heat conductivity, of ionic and molecular compounds. Okay, the two different types of compounds: ionic compound versus a molecular or covalently bonded compound. You distinguish the characteristics: melting point for ionic compound versus covalently bonded compound. The conductivity of an ionic versus a covalently bonded compound. That's what we're asking you to do there. All right, let's get started. First off, remember ionization. Okay, when you have a metal that gives up one or more electrons to a nonmetal. Okay, so not only do we have our basic definition of ionization, which we got from our ionization energy trend, right? Ionization energy was the amount of energy required to remove one electron from a neutral atom. Ionization involves both a nonmetal and a metal. Okay, so we're giving up one or more electrons in this transfer. The reason we're having this transfer is to get both atoms, the nonmetal and the metal, to end up with 8 valence electrons. Remember, the nonmetal, it's going to gain the electron to get to 8. The metal is going to lose the electrons to get to 8. Remember that the octet rule? That's the driving force behind this. An ionic compound, therefore, is going to be composed of positive and negative ions that are combined so that the numbers of positive and negative charges are equal. If there are 2 negative charges, there are 2 positive charges. If there are 3 negative charges, there are 3 positive charges. If there's 1 negative charge, there's 1 positive charge. There has to be the same number of positive and negative charges. They have to balance. Those charges have to be equal. So we have a way to put that last definition into play. Is this thing a real ionic compound? Okay, magnesium and nitrogen. If we ionize both of these using the rules that we've learned about main group numbers, we know that magnesium is going to form a +2 because it's a metal in main group 2, and nitrogen, being a nonmetal, is going to form a -3. It's going to form a -3 charge. Whereas the thing, the charges are not equal. We have a +2 and a -3. They're not equal and opposite. We have to adjust the numbers of each of these ions we have present in order for this to be a real compound. So there is no such thing as MgN. That doesn't exist. However, Mg3 in 2, denoted by these subscripts right here, does exist. Because if each magnesium has a +2 charge, and I have 3 of them, that means that I have a total of 6 positive charges. If each nitrogen or nitride ion has a -3 charge, and I have 2 of them, that's a -6 charge. So now I have a total of 6 charges on either side. That's equal. This compound can exist. And if those numbers don't match, that's not a real thing. That's not a real compound. So looking at ionic bond formation. So we have 2 atoms. They start off neutral, and the metal is going to donate its electron or electrons to the nonmetal, and that's represented here in this animation by the transfer of the electron cloud. And you can also see the trend with regard to ionic radius at play here. Metals, cations, they're smaller than the neutral atom. nonmetals, anions are larger than the neutral atoms. But what we're seeing here is neutral atoms coming close to one another. As they get close to one another, electrons are transferred from the metal to the nonmetal. It's always that direction, never the other way around. And then they stick to each other because of those electrostatic forces that they now have, right? The nonmetal is negatively charged, the metal is positively charged, just like magnets, electrostatic forces. So an ion, once we've made that ion, is any atom with more or less electrons than it's supposed to have. And note, when I say supposed to have, I'm referring to the number that, remember that the number of electrons that it's supposed to have is equal to the number of protons if the atom has a neutral charge. So when I say supposed, I'm just talking about electrically neutral, and that's going to equal the number of protons, which is the atomic number. Also remember, metals will tend to lose electrons to become positively charged cations. So what that looks like, we have this normal sodium atom, okay, 11 protons, 11 electrons. It's going to lose 1 electron. It's in main group 1. And it's going to become a sodium ion. It still has 11 protons because it's sodium, but it only has 10 electrons, which gives it an overall positive 1 charge. Looking at the other side, looking at nonmetals, they tend to gain electrons and become negatively charged anions. So if we start with a neutral atom of chlorine, 17 protons, 17 electrons, this is going to gain 1 electron because it's in main group 7. And that's going to result in a type of chlorine that still has 17 protons because it's still chlorine, but now it has 18 electrons. And this has become a chloride ion. Let's talk about naming a little bit. You guys might have caught on. You might have thought that I mispronounced chlorine there. Let's talk about how we name some of these things. Sodium plus 1 is called a sodium ion. I can say sodium ion, and you know that I mean sodium plus 1 because it only forms 1 charge. The plus 1 means that it's lost an electron. Sodium plus 2, that's called a magnesium ion. The plus 2 symbol means that it has lost 2 electrons, right? We have pretty good grasp on that. But moving to the negative side is where we see something a little bit new. Sulfur minus 2 is called a sulfide ion. Again, the negative 2 means that it has gained 2 electrons. Chlorine, like I said in the previous slide, is called a chloride ion. Negative 1 means that it's gained 1 electron. And so when we have these monatomic, meaning you have one of them, okay, it's just one sulfur atom, one chlorine atom, one nitrogen atom, or whatever, but monatomic ions that are negatively charged, right, over on the right side of the periodic table, we take the last syllable off of the name, replace it with IDE, ide. So we have sulfide, chloride, selenide, bromide, and on and on and on. We also have, in addition to monatomic ions, we have polyatomic ions. And it's a group of atoms that overall they have a charge. They act like they're one ion, and they act the same. So we have an ammonium ion. Yeah, this is a plus 1 charge, but it acts as a unit. This is a carbonate ion, has a minus 2 charge. It just acts like one unit. It doesn't act like individual, 4 individual atoms there. It acts as one unit. And then phosphate has a minus 3 charge. Yeah, again, acts as one unit, as one ion. To demonstrate that, polyatomic ions act just like any other negative ion when bonding. So if we go back to the example we used with magnesium bonding with nitrogen, I have sodium and then sulfate. Okay, we have a sodium and a sulfate, and these are going to ionize. Okay, so that the sodium is going to form a plus 1, sulfate is going to form a minus 2, and there is a way to figure this out, but the thing that you're going to use the most often is that table that is on the back side of your periodic table. It's called the polyatomic ion sheet. You can look up SO4 if you can find it, and you'll see that it has a negative 2 charge. Well, again, the 2 charges, the oppositely charged ions, must have the same magnitude of charge. Here we have sodium plus 1, sulfate minus 2, not the same magnitude of charge. So what we do is we take these charges, and this is a shortcut I'm going to show you. Take that 1, move it down as a subscript for the whole sulfate. Take the 2, move it down as a subscript for sodium. So to really have sodium sulfate, as an actual ionic compound, you're actually going to have Na2 SO4. You're just going to have, and I'm not drawing the 1 here because the 1 is implied, but you need to have 2 sodiums for each single sulfate in order for the charges to match. Again, showing that same trick, I have aluminum, which is going to form a +3 charge, and I have what's that, nitrate, that's going to form a -1 charge, not equal in magnitude. So I'm going to cross those charges down. So the 1 from the NO3 is going to go down to the subscript of the aluminum. The 3 from the charge of aluminum is going to go down the subscript for the NO3. I'm going to be very tricky and put that NO3 in parentheses to make sure that that red 3 that I have there denotes the entire polyatomic ion as a unit, and so you don't mistake it as being 1 nitrogen and then 33 oxygens. All right, we're going to finish up talking about properties of ionic compounds. Ionic compounds, when they're in solids, they form a crystalline structure, which is a regular repeating arrangement of ions in a solid. When they're in this situation, in this arrangement, they are very strongly bonded together, That makes the structure very rigid, and along with one more thing we'll demonstrate here in a few slides. And also, one thing that you need to be aware of is that they have very, very high melting points because of those strongly bonded ions, right? It takes a lot of energy to overcome the forces that bind that solid together to allow it to become a liquid. So here's a representation of a crystalline structure. We see we have positive cations sticking to negatively charged anions, just like magnets. And you see this regular repeating arrangement. Positives are next to negatives, negatives are next to positives. You are not seeing positives next to positives or negatives next to negatives, right? Because, again, they would repel. Now, it's going to be a very important characteristic, conductivity. Okay, do they conduct? Conducting electricity is the same thing as allowing charges to move. If charges can move, meaning electrons here, if electrons can move, that thing can conduct electricity. Now, in a solid, like we just saw on the last slide, those ions are locked in place. They're locked in this crystalline arrangement. And so that makes ionic solids insulators. They don't conduct electricity. But if we are able to melt them, right, so the individual ions can move around freely because they're not locked in place, that can conduct electricity. So melted ionic compounds conduct. But first we have to get them to be very, very hot. Remember, they have very, very high melting points. Or we can simply dissolve those solids in water. That allows them to move, they dissociate, and then they can conduct electricity. I also want to try to describe real quickly why ionic solids are so brittle. Okay, they're very, very strong, but if I introduce some sort of force to it, you're going to see that it quickly breaks. Now notice here in this representation, I have this alternating positive-negative matrix here. The positives are always next to negatives, negatives are always next to positives, and so there's a huge attraction here, huge attraction, very, very strong. But if I'm able to introduce a force coming from this direction and just slightly offset these ions so that this positive is on top of this positive and this negative is on top of this negative, all of a sudden the repulsion force that we're experiencing because of those electrostatic interactions is going to, they're going to repel each other and they're going to shoot apart. They're going to break very, very readily. And so it looks like this whole sheet comes off. Okay? And this is why we say strong repulsion breaks crystals apart. All right, that's going to do it for section 3. We'll take up section 4 next time we meet. I will see you next period.